This video is on the chi-squared goodness of fit test. The goodness of fit test measures how closely the observed data fits with the expected data for a particular distribution. In a chi-squared goodness of fit test, then the degrees of freedom is just n-1, so that's however many data sets you have, and then -1. The students in year 8 are asked what day of the week their birthdays are on this year. The table shows the results. Part A, write down the table of expected values given that each day is equally likely. So when you're doing a chi-squared goodness of fit test, you need observed results and you need expected results. So for the expected, we need to work out how many students we have in total, which means just adding up all the values of the current frequencies, and then dividing by how many days we have, which is 7. And when we do that, you'll find out that the expected frequency for each day would be 15. So there's 105 in total, divided by 7, which means we would expect there to be 15 each day, considering that each day is equally likely. B, conduct a chi-squared goodness of fit test at the 5% significance level for this data. So to do this, we need to first of all state what our null hypothesis is, that the data satisfies a uniform distribution. So what that's meaning is that all our values are similar to our expected values. And then our alternate hypothesis that the data does not satisfy a uniform distribution. We also need to work out our degrees of freedom. So here we have 7 bits of data because we've got 7 days. So our degrees of freedom would just be 7 minus 1, which equals 6. From there, then we can go to our calculator to work out our chi-squared value and p-value, and I'll show you how to do that now. To calculate the chi-squared goodness of fit test on your TI Nspire calculator, go into the Lists and Spreadsheets document, and we are going to enter all our observed data into one column in the table. We are then in the next column going to enter our expected values. From there, go to Menu, Statistics, Stat Tests, chi-squared GOF, which stands for goodness of fit. Our observed data is in column A. Our expected data is in column B. Our degrees of freedom, as we have 7 columns or 7 bits of data, our degrees of freedom will be 6. Then we'll have our results in column C. Click OK. And you will see here we have our chi-squared value of 1.6, the p-value of 0.9525, etc. And our degrees of freedom is 6. And that's how you do a chi-squared goodness of fit test. After putting it into our calculators, we find out that the chi-squared value is 1.60 to 3 significant figures, and the p-value is equal to 0.953 to 3 significant figures. Part C, we want to write down the conclusion, so we can do 2 things here. We can compare the chi-squared to the critical value or the p-value to the significance level. You can do either of those, but given both values, so you choose whichever you would prefer. I will write down both though. So in this one, our chi-squared of 1.60 is less than the critical value of 12.592. Or as I said, we can do the p-value, which is 0.953, and compare that to the significance level, which is 5% from part B in the question, and that is greater than 0.05. Now both of those, that tells us that we will be accepting our null hypothesis. To accept, the chi-squared has to be less than the critical value, or the p-value is greater than the significance level. Example 2. The scores for IQ tests are normally distributed with a mean of 100 and a standard deviation of 10. Cynthia gives an IQ test to all 200 IB diploma program students in her school. The results are shown in the table. Cynthia wants to test whether these results are also normally distributed and performs a chi-squared goodness of fit test at the 10% significance level. First of all, we're going to write down the null and alternate hypothesis. So our null hypothesis will be that the data is normally distributed, and our alternate will be that the data is not normally distributed. Part B, find the expected values. So now we have to use our normal distribution feature on our calculator to work out our expected. So what I'm going to do here is I'm just going to go to the table and I'm just going to add some columns to it. And I'm just going to add a probability column and an expected. Now in our calculators you've got to do the normal CDF for each of these, and if you do that you will get the following probabilities. From there we multiply each of these by 200 as there's 200 students to find out what we would expect for each IQ score. And if you do that, you'll get these values. So here I'll just write in for your TI Inspire calculators, you'll be doing a normal CDF with the lower bound from the class, the upper, and then your mean and standard deviation. And then to find the expected, we multiply that by 200 to get our expected out of 200. Now with chi-square tests, this won't come up in IB exams, but it could come up in your IA if you decide to do a statistics IA. If that is the case, with our expected values, we cannot have values that are less than 5. So you will see here we have 2 that are less than 5. When this happens, we need to combine scores so that all our expected values are above 5. But if we were to combine 4.28 and 0.270, that would still be less than 5, which means we need to then combine those two with the one above, with the 27.2 for the 110 to 120 class interval, and then we'll have all our expecteds above 5. So I'm going to now create a table with our new sections, which will include our combined ones, and you'll see how that works. So our first score will still be when x is less than 90, because we don't need to do anything with that. Our observed was 5, just from the table up above here. And our expected frequency is 31.7, which we worked out before as well. So that's what I'm doing here, just creating this table. The 90 to 100 is fine. The observed is 14, expected is 68.3. 100 to 110. 74 for observed and 68.3 for expected. Now the last one, we need to combine the last three, so this one it will just be that x is greater than or equal to 110. We add all the observed for the final three, which would be 107, so 58 plus 34 plus 15. Add up all the expecteds and we would get 31.7. Now all our expecteds are above 5, which means we can do a chi-squared. So sorry, the table before with the combined is actually part C, and the table added here up the top with the expected values, that's part B. So part C is rewriting the table with any values less than 5. That's what we've done there. Part D, we want the degrees of freedom. So our degrees of freedom is number of data points minus 1. We need to go to our new table. So this one here. And we have 4 sets of data points, so it'll be 4 minus 1, so our degrees of freedom equals 3. Part E, we're then told the critical value is 6.251, find the chi-square statistic and the p-value, and state the conclusion. So go to your calculator, follow the steps we did before with the new table with Drew to find the chi-squared and p-value. So use the exact same steps as example 1. And we'll find that the chi-squared equals 245. The p-value equals 7.89 times 10 to the power negative 53. So just always double check, actually go into the value on your calculator and double check down the bottom that there's no scientific notation present. And then we can do our conclusion. So we compare our chi-square to the critical, so 245 is greater than 6.251, or the p-value 7.89 times 10 to the power of negative 53 is less than the significance level. If we go back up to the question, that is 10%. So that's less than 0.1. And if we do that, therefore, we're going to reject the null hypothesis. Example 3. So using what you learned in chapter 7, so that's just normal distribution and binomial distribution. The probability when you toss 3 coins of obtaining 0 heads, exactly 1 head, exactly 2 heads, or 3 heads Hagar tosses 3 coins 200 times and makes a note of the number of heads each time. The results are as follows. She's interested in finding out whether her results follow a binomial distribution and performs a chi-squared goodness of fit test at the 5% significance level. Using the binomial information here in the thing of 3, 0.5 and the fact that Hagar tossed a coin 200 times, find the expected values of the number of heads. So this is just using your calculator in the binomials. And for each of these, you would do a binomial PDF because we want the exact value. You're going to have 3, 0.5, and then you're going to have all your individual values. So we've got number of heads is 0. And you do that for each of them for 0, 1, 2, 3. It will tell you the probability of each of them. We'll just add to the table here. And we'll find the probability as are 0.125, 0.375, 0.375 and 0.125. And to find out expected, multiply those by how many times we're costing the coin, which is 200. So times by 200. And then we'll find our expected values are 25, 75, 75 and 25. B, comment on whether any of these values are less than 5. That we can look at our expected and say none of them are less than 5, they are all greater. Part C, write down the null and alternate hypothesis. So the null hypothesis will be the data follows a binomial distribution, or the number of heads follows a binomial distribution. The alternate will be that the data does not follow a binomial distribution. D, find the chi-squared value and the p-value. We're also going to need the degrees of freedom, so degrees of freedom will be 4 minus 1, which equals 3, because we've got 4 bits of data. Do our chi-squared step, just as we did in example 1 on the calculator, and you find the chi-squared is 2.426, and the p-value is 0.489. Then we can do our comparisons for part E. So the critical is 7.815, so 2.426 is less than 7.815, or we're looking at the 5% significance level. 0.489 is greater than 0.05. Therefore, we will be accepting the null hypothesis. And that's the chi-squared goodness of fit test.